Hello YouTube! We're going to finish out our forces unit by talking about systems of objects. So in particular, these are when you have multiple things pushing on each other and moving together, and how you can use those two things to really simplify problems that can get insanely complicated otherwise. Um, yep. So, in particular, if you are able to model the motion of groups of objects, that's the primary focus, especially things that are moving together. And also, if they're moving together with a rope connecting them, that's the other big one. This is going to be a lot of using Newton's third law, just as a heads up. Ideally, end of the day, you should be able to identify which of the forces are going to be trying to get things to be going forward, which of them are trying to get things to go backwards. And as far as forward and backwards goes, it's pretty loose. But just really taking track of like changing how you're thinking so that instead of having it be purely directional, it's based on reassessing the directions to make the problem easier, much like how we did with hills. And then from there, making a combined free body diagram that includes all of the forces so that you've simplified the problem down to just treating it like it's one object. And that's sort of the trick. So let's say we've got an example problem like this one, and then we'll sort of go through how you would do it traditionally, and at least a little bit, and then from there go into, I'm going to get rid of this in a second. Ooh, no. I'm going to get rid of this in a second anyway, so I don't know why I'm bothering to move my face, but whatever. And then we'll go into sort of the shortcut for how you do it much easier. So, we've got a setup where we've got 3 boxes. One of 5 kilos, one that's 10 kilos, and then a third 5 kilogram box. I really should be doing more of these without numbers in hindsight. I'll probably try to do that going forward in future units. I think it's something we should probably ramp up to. In any case, we also have a person who has freakishly long arms and is pushing the box 1 with a force of 80 newtons. And this is box 1, box 2, and box 3 and C are not the same thing, but here we are, box 3. And we are asked for, this is problem 1, and this is unit 2.8. This is problem 1, and we are being asked for the acceleration of box 2. Oops. So, for this one, we're pretty much, what's weird about it is we have 3 different objects. So if we do what we would traditionally do here, we're going to make a free body diagram for box 1, a free body diagram for box 2, and a free body diagram for box 3. And this is not completely wasted effort once we do the shortcut, but most of the time this is going to be a bit more than you need to do. So for box 1, we'll have gravity, pretty much same as always with M1. We'll have the normal force from box 1, and we'll have everything that's touching it. So we've got the person touching it, pushing it to the right. I did not leave myself enough space. It's okay though. We're just pushing with 80 newtons. And we've got box 2 pushing back on box 1, so force of 2 on 1 going to the left, which if you wanted to be really careful about it is a normal force. For box 2, which I guess I'll do over here, we've got the force of box 1, which is touching it, pushing it to the right. So this is the force of box 1 on box 2. And we've got box 3, which is touching it, pushing it to the left. So this is the force of box 3 on box 2. And technically, well, we'll get back to that. We've got the mass of box 2 with gravity, and we've got the normal force from box 2 going up. And then finally, for box 3, we've just got box 2 touching it, so the only thing pushing it is box 2 pushing box 3. And gravity going down, which this should be a bit smaller, and normal force going up. All right. So those are our free body diagrams for all of them. From there, what we would do is we would set up a system of equations for each. So for box 1, we would set up a system of equations where in the x direction, we would have force from the person minus force to 1, and that would equal mass times the acceleration of box 1. For box 2, we would set it up so that we would have our force of 1 on 2. That would be positive because it's going to the right. We would have the negative force of 3 on 2 because that's going to the left. That would be equal to mass times the acceleration of box 2. For box 3, we would have a setup that looks much the same, except for this one would be just box 2, 3 equals MA3. And so what we would do from here is we would have to say that because all 3 boxes are moving together, acceleration from the first one equals acceleration from the second one equals acceleration from the third one. And that's the big trick. And I'm just going to call that the acceleration. And so if we make that substitution so that all of these are just acceleration, then we'll have a system of equations. And in our system of equations, additionally, by Newton's third law, we can make some more headway, but I'm skipping a step. So in our system of equations, we'd have a setup where our only variables are F23, F32, F12, F21, and then the thing we're actually looking for, which is A. Yuck. There's another trick, which is that F21 equals negative F12. Well, why is that? Well, Newton's third law pairs. These two are caused by the boxes pushing each other, so those two are paired. Additionally, these two are caused by the boxes pushing each other, so those two are paired. And so I can additionally say that the force of box 3 on box 2 is equal to negative the force of box 2 on box 3. Although actually the way that I've set up my equations, I actually took care of the signs internally within the equations. So I wouldn't want to use a negative sign here when saying that they equaled each other. I would just say their sizes are the same. I took care of the positive or negative when I set up my Newton's second law equation, which is my preference because if you keep the negative sign hidden within the variable, it tends to, for me anyway, wind up being more confusing than just explicitly forcing it to be positive or negative based on whichever direction it should be going, for reasons like this. So now what I can do is I can swap all these out within these equations, and then I will have 3 equations, 3 variables. I can set up a system of equations. I can chain together F21 in terms of things that I want and things that I know, FP and A. I can plug that in over here and get F32 in terms of FP and A, and then plug that in over here and finally get an answer. No, I think I'd be able to solve it just here. Yeah, because it would only be in terms of givens if I plugged it in here. So I could plug it in over here, and then I would be able to solve for the acceleration, and once I had the acceleration, I'd be good to go. Yikes. So that would be the process if you want to do it the slow way. If you want to take a shortcut instead, and this shortcut is especially good for getting the acceleration of multiple objects, what we can do is we can pretend that all 3 boxes are glued together, because effectively, if they're moving together, all 3 boxes are glued together. If we do that, we'll have one box that's box 1 plus 2 plus 3. That box is being pushed by a person. We've got a 5 kilogram block, a 10 kilogram block, and a 5 kilogram block all glued together. If I draw a free body diagram for this block, we'll have gravity on all of it, so m1 plus m2 plus m3 times g. We'll have normal force going up, for 1 plus 2 plus 3. And I'm going to draw the forces that stay first, And then I'll talk about what happened to F2.1 and F1.2 and F3.1 and 3.2 and F2.3, because sometimes, especially when you get into stuff with pulleys, it won't be quite this nice, and you should actually be careful about including it all. So in particular, we've got that 80 Newton force from the person going to the right. That's it. The only thing pushing all three boxes, if you think of them as one unit, is that person. Now there are some other forces that are here. In particular, if we think about F2.1, F1.2, which goes to the right, and F2.1, which goes to the left, those are there. But by Newton's third law, they're always the exact same direction, size, and the exact opposite direction. So they cancel, and I don't have to care about them. If we look at F3.2 and F2.3, same thing. Newton's third law pair, and they cancel, so I don't have to care about them. So when I'm setting up my equation in the x direction, the only thing I'm left with is that my net force in the x direction is the force from the person, and that's it. And that'll need to equal the mass of the system, meaning the group of objects, and that'll be multiplied by the acceleration. And so if I want to solve for the acceleration, the algebra is insanely easy comparatively, because I just have to divide by m1 plus m2 plus m3. And that'll give us this friendo, boop, 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 which we've got 80 newtons divided by our 20 for combined mass, because we've got 5 plus 10 plus 5, which gives us 4 meters per second squared as our acceleration. And that's it. Now, if you were then asked about what's F1.2, what's F2.1, the problem is that if we're looking here, well, we got rid of it, so we can't use it. Oops. What we could do instead, though, is once we've found this acceleration, these equations up here get a lot easier. And so what you can do to find the internal forces that are being canceled out by treating it like a system is come up here and plug in that acceleration, and then use that acceleration with one of the individual equations to find one of those individual forces. If you were looking for F2.1, the only variable here is F2.1 once you know acceleration, so this would be a great one to use. If you're looking for F2.3 or F3.2, because they're the same as each other by Newton's third law, you can use this one because the only variable is the acceleration, and so if we plug it in, we're just good to go, we'll have it. And that would be the way you can figure out the internal forces. So this part is still useful, depending on what you're trying to do, but especially if you're just trying to find the acceleration of an object, and you know about what external forces there are, but you don't know about how the objects within the system are interacting with each other. Just lump them all together into one object, and suddenly it's not a system, and it's nowhere near as complicated. So I believe there's a slide, great, that just sort of says all that in words. So when multiple objects are sliding together, they all have the same acceleration. This makes the modeling a lot easier because you can basically treat all of them as one connected object. The big thing is that you draw a combined free body diagram for all of them. Make sure that when you do that, you pool all their masses and treat it like one combined mass. Writing out the variables for each mass and being like m1 plus m2 plus m3 plus however many m's there are in parentheses before you multiply by acceleration is the big place where that'll happen. In particular, for each object, determine which direction is forward. That might seem a little weird if they're all moving together, but when we get to pulleys, that way of thinking of it makes more sense. You don't have to include any internal forces because they should cancel out. There's a couple exceptions to that, especially for like physics C, but for the AP1, probably not going to deal with any problems like that. If it's going forward, draw them to the right. If it's going backwards, draw them to the left for the external forces. If it's going perpendicular to the direction of motion, draw those ones as vertical on your sheet. So you're basically taking the hill thing where you were rotating the way you were thinking about it, and you're doing that for each individual object so that forward is to the right, backwards is to the left, and into or out of the plane of motion are perpendicular to that. In theory, all your perpendicular stuff will cancel out, and your external forces should be making it so that you have a much easier problem to deal with. I'm trying to figure out if it's worth it to show an example of when they don't cancel, and I think it might be a little bit. So if we go back to that last one for a sec, in particular, if we were to look at that same one but with friction, if you look at all of the individual ones, they'll look the exact same as they did before. But now on each one of them, there'll be a little bit of friction. And that little bit of friction on each one of them will be using the friction equation. So using that Fn equals, force of friction equals mu k times Fn. And if you then go ahead and lump that together as a system, what's interesting about it is you could either think of it as the way you were before, where you've got Fn of 1 plus 2 plus 3, or you can think of it based on the combined gravity of the system. One sec. Getting a little bit ahead of myself. In this case, you'll have the normal force going up, which needs to be the same as the combined mass times gravity. Or you can think of it as all three normal forces separately added together. So you'll have Fn1, Fn2, and Fn3. But those two things need to be the same as each other. You'll also have three separate frictions, all going to the left, because you want to keep every single external force from all three of them. So you'd have the three frictions going to the left, and then you'd have the force of the person going to the right. What's interesting about this is because if we set up our three equations, we'll have Fn1 times mu, Fn2 times mu, and Fn3 times mu. And that'll equal the force of friction on the first one, the force of friction on the second one, and the force of friction on the third one, respectively. What's neat about this is if I take these three equations and add them together, we'll have the force of friction 1 plus force of friction 2 plus force of friction 3. And the reason I can do this is because the left half of an equation is always the same as the right half of an equation. So if I add the left half and the right half to the left half and the right half of this one, I haven't broken equivalency because F1 is the same thing as mu Fn. It's like adding 1 plus 1, except 1 plus 1 is represented in a more complicated way. If I know that x equals 1, I can add 1 to one side and x to the other side because both of them are just 1. I haven't changed it. It just looks weird. Same thing over here on the right. What's interesting about this is that if I factor out mu from all three of these, we'll have actually just kind of proved that we've just got their combined normal force, which we already know based on what we were talking about earlier, is the same as if I was just thinking of one normal force from the full combined object, which has to be balanced with the gravity from the full combined object in order for it to not go through the table. And what's interesting about that is that's actually pretty much just the same as saying, I'm just going to ignore that there's three separate frictions and pretend that there's just the one friction that's from the normal force from all three of them. And that'll be that the combined friction of on all three. And so this is actually kind of a way of proving that if they're all sliding together, you can still treat it like it's one object that has the friction it would have if it was one object, as long as they're all made out of the same thing and as long as they all have the same coefficient of friction. So again, systems can be really useful if you needed to include friction here, because if, and this is a fairly big if, they all were made out of the same material and all had the same coefficient of friction, this coefficient of you could use that to have just one combined force of friction and use that to find the acceleration by just using one force of friction with the one normal force and the one coefficient of friction. But again, that only works if they have the same coefficient of friction. If they have different coefficient of frictions, you will have to find the combined force of friction by just using the separate coefficient of frictions from this part of the equation and just saying that'll be equal to the combined friction. The forces will add linearly, so you don't have to do anything weird with so you can actually do that and that'll work. Little more complicated, hopefully, than most of the stuff you'll have to deal with, especially on the AP exam. AP problems tend to be designed such that they should be solvable in about 20 minutes, which pretty heavily limits the amount of stuff they can put on there. But just in case, I wanted you to see that before we move on to our last bit, which is pulleys. So if we're dealing with pulleys, they kind of make things terrible and confusing. Basically, the way that a pulley works, if it's an ideal pulley, is that you're taking this object that can rotate, and it can rotate completely freely, no friction, thankfully, no mass, thankfully. Otherwise, you have to use much, much more complicated stuff. And you're taking this rope. And what the rope does is it lets force for reaction pairs change directions when in combination with a pulley. Because normally, the reaction pair for one would need to go up and the reaction pair for the other one would need to go down. But what a pulley does is it lets it say, yeah, there's still a reaction pair, but one of them will go up and one of them will also go up. Which makes your math miserable. Cheers. Unless you do one really quick additional trick for the focusing on forward-backwards like we have like I was saying for systems, and that's why I was saying it, is because that one change of thinking of it as forward and backwards really helps a lot. So in particular for this one, we've got a 10 kilogram block, we've got a 5 kilogram block, we've got a pulley, and we're asked to find the acceleration of the system. Okay, so I'm going to go ahead and label this block 1. I'm going to go ahead and label this block 2, just so I've got something to work with and keep it a little more neat. So doing a free body diagram separately for each of them, we've got block 1, which is getting pulled up by the force of tension, and we've got block 2, which is getting pulled down by M1G. And we've got block 2, which is getting pulled up by the force of tension, and getting pulled down by a smaller M2G. Now, because these are both ends of a rope, and ropes are just going to have a Newton's third law pair, these are paired and need to always be the exact same as each other. What's particularly weird about this one is that, yes, they are moving together, but every time one goes up, the other one goes down. So if I'm trying to solve it in a more traditional way, the acceleration of 1 is equal to the negative acceleration of 2. I set up my equations for 1, which will be that Ft is going up, M1G is going down. That'll equal M times A1. For the second one, it'll be Ft is going up, Mg is going down. That equals M2A2. 2. And you can solve this by replacing a2 with negative a1. When you do that, you'll have a system of equations with two variables, two equations, two variables, and you can solve it. Personally, I don't like that way because it's harder to keep track of the pluses and the minuses, and it's a lot more algebra. If we do it with systems and we start thinking about how these things are getting pulled forward and backwards, it gets a lot easier. Because if we think about it as a system or a group of objects where these two things are moving together, right? So, I mean, basically they're glued together. I'm going to pick a direction and say that rotating so that it's going, and I'm going to have to watch the camera for this to make sure I don't do it mirrored. Yeah. So I'm going to do it such that this direction is forward. So when block 2 goes up, that's forward. So rotating like this is positive. And then I'm going to think about, when I'm drawing my combined free body diagram, which of these forces are trying to get it to rotate forward, and which of these forces are trying to get it to rotate backwards. This one is trying to get it to rotate like this, which I said was forward. So I'll have m2 times g trying to get it to rotate forward. I'll have m1 times g, which is a bit bigger, trying to get it to rotate backwards. The force of tension on the first block is trying to get it to rotate this way, so that's forwards. The force of tension on this block is trying to get it to rotate backwards. So what's nice about that is that those two forces of tension cancel out because they're a pair and they're going opposite directions when we think of it like this. Which is really nice because if I set up my equation for my combined system of mass 1 plus mass 2, what we'll get is something that looks like this. Our net force of 1 and 2 needs to equal the mass of 1 plus the mass of 2 times acceleration. Our net force is m2g going forward and m1g going backwards, and that needs to equal m1 plus m2 times a. This is nice because if we look at our old equation, we didn't know ft, we didn't know ft, we didn't know a1, and we didn't know a2. We knew a relationship between the two of them, so we could use that to swap it, so we only had two variables and we can solve. So it was technically a system of 3 equations, 3 variables, which is solvable but annoying. If we look at this setup, based on our little bit of extra effort where we thought about one of them is going forward, one of them is going backwards, and the tension's canceling because one goes forward and one goes backwards for like the way it's trying to rotate, then we wind up with something where our only variable is a because we know all the masses and g is just 10. And so the algebra here is really nice because I just have to divide each side by m1 plus m2. If you want to get really fancy, you can factor out the g, which I don't think I'm going to do just so that I don't lose people. And there's our answer. We know that m2 is 5. We know that m1 is 10. So we'll wind up with 50 minus 100, so negative 50 over 15, which is 5/3, so should be like 1.6, but no. 50 over 15, and let me double check that I did that right. Great. Is, oh yeah, it'll be 1/3 gravity because you have 3 parts of 5 being fought against by 1/3 of 15 and fought with 4 by 1. Yeah. There's some weird stuff you can do with proportionality here to solve it as like a shortcut for when you've done this too much. Now this will be negative, so we'll get negative 3.3, and I'll round it there, meters per second squared. If you wanted to leave it as 10/3, that's actually probably a better way to do it. Especially because that's g over 3, is another way to think of it. So we have 1/3 as much acceleration as if they were just falling. And what that negative means is just that it's not going. I said that this wave was positive, so it just means that it's rotating, or sorry, it's accelerating towards the heavy one. If it was already moving up, it would be slowing down in the process of gradually stopping and then going back like this. If it's moving down at the beginning, it'll be gradually going faster, and if it starts from rest, it'll start accelerating and moving in that direction. And that's a way to make that one a lot easier. Again, if you want to find the tension, what you could do is go back to either of these two setups. Now that you know the acceleration, it's really easy to plug it in and find the tension. Or at least much easier than it was before. The reason in particular that this is incredibly useful is for when you get to weirder problems, like one where you've got something like this, where you've got like a cart on wheels that's on a table, and then they've got this pulley with a mass hanging off of it. What you can do here is you can still think of forward, backwards, and that's sort of the key for this one, is when you're setting up your combined mass for like M1, M2, you can still think of it as the tensions canceling out, as long as you're like, okay, well, this tension goes forward, this tension goes backwards, this gravity goes forwards, and the gravity on this one and the normal force on this one cancel out, so I don't have to care about them. You could even do that if you added in friction here, as long as you could figure out what the friction was. And you could even put it on a hill. And again, as long as you're thinking of forward, backwards, your tensions will cancel out and your equations will get much easier for it. Yeah. So that's pretty much it. Thanks for watching. Goodbye, YouTube.